Jai Hind, dear children. Today we are going to discuss about Wheatstone Bridge, a special design made by the scientist Charles Wheatstone. Now we can study what is Wheatstone Bridge. Wheatstone Bridge is a combination of capacitors or resistors in the form of a bridge, or the design is in the form of a bridge. And this design was made by scientist Wheatstone, and hence the bridge is called Wheatstone Bridge. So the bridge consists of 4 resistors arranged in the form of a bridge. So across B and D a galvanometer is connected, and hence it is called a galvanometer arm. And across A and C a battery is connected, and hence AC is called a battery arm. Okay, so here how it acts as a bridge across AC. Here this is AC, this is also AC. So between A and C a bridge is connected, and hence it is called a Wheatstone Bridge. Now what is the use of this Wheatstone Bridge? Wheatstone Bridge is used to find out unknown resistance using a very important device called a meter bridge that we will study afterwards. Now we can solve the condition for Wheatstone Bridge. For this, here for the loop we can consider the loop A, B, D, A. Here from the cell I is the current coming, and at the junction A current splits into I1 and I2, and I1 is the current moving, and at the point B again current splits to form Ig and I3, and Ig is the current flowing through the galvanometer, and the galvanometer it has resistance G, and this Ig current and this I2 current at the point D again they combines to form I4. I4 is the current flowing through R4, and I3 and this R4 combines to form I. So that is the division of current. Now we can apply Kirchhoff's rule, Kirchhoff's loop rule for the loop A, B, D, A. We can consider any direction, clockwise direction or anti-clockwise direction. Here I have taken the clockwise direction, A, B, D, A. How will you apply the loop rule? We can apply the loop rule like this. Here I1, R1. Okay, so this is the original current and this is the assumed direction of current. Both are same, therefore I1, R1. Here the current is flowing in the downward direction, therefore plus Ig. G represents the galvanometer resistance. And here the current is moving upward. Original current is moving downward, but assumed current is moving upward. Okay, so it is in the opposite direction. So according to the sign convention, it is minus I2 R2 equal to 0. Okay, so that is the Kirchhoff's loop rule in the loop A, B, D, A, for the loop A, B, D, A. Now we can apply the same Kirchhoff's loop rule for the loop B, C, D, B. Here also we can consider clockwise direction is the assumed direction of current. Current is flowing in this direction clockwise. What is the potential difference across R3? I3, R3. Okay, it's positive, same direction, therefore positive. Therefore I3, R3. Now here the current is flowing in the downward direction, assumed current, but original current is in the upward direction. Okay, opposite direction, therefore it is minus I4 R4, and through the galvanometer also opposite, therefore minus Ig G equal to 0. Okay, so that is the method by which we can apply Kirchhoff's loop rule for the loop ABDA and BCDB. Now the bridges you mainly use when it is in the balanced condition. So bridge is balanced means the current through the galvanometer, that means Ig equal to 0. When Ig equal to 0, the potential difference across BD equal to 0. So that is the balanced condition of the Wheatstone Bridge. This is the first equation and this one is the second equation. Now we can say bridge is balanced, the Wheatstone Bridge is balanced. Bridge is balanced when the current through the galvanometer is equal to 0. When current through the galvanometer equal to 0, then potential at the point B and the potential at the point D are equal, or potential difference across BD equal to 0. Okay, so if you substitute that condition in the first equation we can take Ig equal to 0. The first equation becomes I1 R1 minus I2 R2 equal to 0, or we can write I1 R1 is equal to I2 R2. I1 R1 is equal to I2 R2. That is the third equation. Right. Now, applying the same condition, balanced condition in the second equation. Here also Ig can be taken as 0. So, the second equation becomes I3 R3 minus I4 R4 equal to 0, or I3 R3 equal to I4 R4. That is the fourth equation. Okay, again in the same balanced condition, current through Ig equal to 0 means I1 and I3 are equal, isn't it? Because Ig equal to 0, no splitting take place here. Therefore, I1 and I3 are equal. Similarly, I2 and I4 are equal. So, bridge is balanced. Then Ig equal to 0. Now, I1 and I3 are equal. I2 and I4 are equal. So, in the balanced condition of the bridge, we can say, so at the balanced condition, of the bridge, I1 and I3 are equal. Similarly, I2 and I4 are equal. Right. Now, the third equation can be written as I1 R1 is equal to I2 R2, and the fourth equation becomes I3 R3 equal to I4 R4. Just divide the two equations. Third equation divided by the fourth equation. So, we can write I1 R1 divided by I3 R3 is equal to I2 R2 divided by I4 R4. Now, I1 and I3 are equal, no? Similarly, I2 and I4 are equal. We can cancel and we can write R1 by R3 is equal to R2 divided by R4. Or we can rearrange it and write R1 by R2 is equal to R3 divided by R4. This is the balanced Wheatstone condition, Wheatstone bridge condition. So, when the bridge is said to be balanced, R1 by R2 equal to R3 by R4. So, here when the bridge is balanced, R1 by R2 equal to R3 by R4. Okay, so this is the balanced Wheatstone condition. So, as I told before, Wheatstone bridge is an application of Kirchhoff's rule, and using Wheatstone bridge we can find unknown resistance using a very important device called a meter bridge. Question relating Wheatstone bridge. In the given circuit, calculate the current drawn from the battery by the network of resistors. Here 4 resistors are given, 1 ohm, 5 ohm, 4 ohm, 2 ohm and 2 ohm. So, here 5 resistors are there, it is arranged in a manner. So, we can redraw the network of resistors like this. Can we arrange them in the form of a Wheatstone bridge? That is a question. Battery of 4 volt. Okay, so this is battery of 4 volt. From the positive of the 4 volt, here this is A, isn't it? So, from A 1 ohm is connected and 2 ohm is also connected, and the other point is B. From from the point B 2 ohm is connected, right. So, the point is C. Okay, here the other end of 2 ohm is connected to C, the other end of 2 ohm is connected to C. Across B and C, what is connected? 5 ohm is connected. So, this resistance is 5 ohm. So, this is 5 ohm. Across C and D, because negative of the cell is connected to D. Across negative and D, this is the point D. Across D and C, what is connected? 4 ohm is connected. Across C and D, 4 ohm is connected. So, this is a pure Wheatstone bridge. Okay. Now, is the Wheatstone bridge balance condition satisfied here? What is the balance condition? R1 by R2 equals R3 by R4. That is a Wheatstone bridge balanced condition. Okay. So, here 1 by 2 equals 2 by 4. So, the Wheatstone bridge balance condition is satisfied. So if it is satisfied, what is the current through BC? The current through BC is equal to 0. Okay, so here the resistance of 5 ohm in the arm BD is considered to be ineffective because current through 5 ohm is 0. Since the Wheatstone's bridge balance condition is satisfied. Okay, so here Wheatstone's bridge balance condition is R1 by R2 equal to R3 by R4. This is Wheatstone's bridge balanced condition. Wheatstone's bridge balanced condition. So here the balance condition is satisfied because 1 by 2 equal to 2 by 4. 1 by 2 equal to 2 by 4. So the condition is satisfied and hence 5 ohm is considered to be ineffective. So since the bridge is balanced, resistance 5 ohm is considered to be ineffective. So resistance 5 ohm is ineffective. Since current through 5 ohm equal to 0. Okay. So current through 5 ohm equal to 0. That means what is the connection between 1 and 2 ohm? Here there is no 5 ohm. Okay, 5 ohm is ineffective. So 1 and 2 are connected in series. 2 and 4 are connected in series. So we can redraw the circuit like diagram like this. Here this is 1 ohm, this is 2 ohm. Here 1 ohm, this one is 2 ohm. Okay, both are connected in series. Then from the point 2 ohm is connected and 4 ohm is connected. So this is 2 ohm, this one is 4 ohm, and here a battery is connected. 4 volt is connected. Now it is easy. 5 ohm is not considered and hence 1 and 2 are in series, 2 and 4 are in series. We can find out the equivalent resistance. 1 and 2 are in series, so equivalent resistance is 3. 4 and 2 are in series, equivalent resistance is 4 plus 2, 6, and both are connected in parallel. Okay, so equivalent resistance can be written as 1 by Rp equal to 1 by 2 plus 1, 3 plus 1 divided by 4 plus 2, 6 equal to 6. We can take the LCM here, 2 plus 1, that is equal to 3 by 6. So equivalent resistance Rp is equal to 6 by 3 equal to 2. That is the equivalent resistance of the circuit. Now we have to find out the total current, isn't it? So total current I equal to V divided by R from Ohm's law. Voltage is 4 and resistance is the total resistance, which is 2 ohm. So hence the current drawn from the battery is equal to 2 ohm. So that is the answer. Another question, the galvanometer in each of the following circuits does not show any deflection. Find the ratio of resistors R1 and R2 used in the two circuits. Two circuits are given. So this is circuit 1 and here this is circuit 2. So in both the case, galvanometer shows zero deflection, null deflection. That means the bridge is said to be balanced. So since galvanometer shows zero deflection, bridge is balanced and hence we can write 4 by 6 equal to R1 by R2, isn't it? Here also bridge is balanced, but here the change is galvanometer and the cell are interchanged. So at the balance condition, if galvanometer and cell are interchanged, it does not affect the balance condition of the Wheatstone bridge. So we can interchange it at the balanced condition. Okay, so here also we can write 6 by R2 equal to 12 divided by 8. Okay, so here the first case we can write balance condition is 4 by 6 equal to R1 divided by 9. Right, 4 by 6 is equal to R1 divided by 9. From this we can write R1 is equal to 4 into 9 divided by 6. Okay children, so it is equal to 6 ohm. And in the second case we can write, here also we can write the balance condition 6 by R2 equals 12 divided by 8. Here also R2 can be written as 6 into 8 divided by 12. So simplify, you will get 4 ohm. we have to find out the ratio of R1 and R2, no? So direct R1 by R2 equals R1 by R2 equal to 6 ohm divided by 4 ohm. So it is equal to 3 divided by 2. So ratio R1 is to R2 is equal to 3 is to 2. So please note the main thing, at the balance point we can interchange the battery and galvanometer. It will not affect the balance condition. So here the answer becomes 3 is to 2. Okay.